Have you ever noticed fruits and vegetables kept at room temperature for several days are often rotten and smell bad? Some chemical reactions take place inside them which spoils them. Hello everyone, we are here today to learn about chemical reactions and equations. In this lesson, we will focus on the basic concepts for a crystal clear understanding and also on important topics from exam perspective. So we will learn about chemical reactions and equations, how to balance a chemical equation, and types of chemical reactions. Do you think it's really important to learn about chemical reactions? Yes, of course. Whenever you are ill, you take medicines and they work like magic and make you feel a lot better. That's because some chemical reactions take place inside your body which make you feel better. Trees prepare their food by the process of photosynthesis, which again is a chemical reaction. We breathe in oxygen to oxidize the food that we eat to get energy. Oxidation of food is again a chemical reaction. Rusting of iron is a chemical reaction. Digestion of food is a chemical reaction. Burning of fuels in our vehicles is also a chemical reaction. So what are we waiting for? Let's get started. Chemical reactions, chemical equations. Are they same or they are different? A lot of us are often confused between the two. So watch this video to get a complete clarity on this. In all chemical reactions, be it rusting of iron or digestion of food, we see that the nature and identity of the initial substance has somewhat changed. We could either notice a change in state, or we could notice a change in color, or evolution of a gas, or a change in temperature. So one of these changes are noticed during the course of a chemical reaction. So let us look at few examples. Let's talk about rusting of iron. So what happens in rusting of iron? We see that the color of the iron particles change from blackish, like generally iron is like blackish grayish color, and it changes to reddish brown color. So what do we notice? We notice a change in color. So rusting of iron is an example where we notice a change in color as the chemical reaction takes place. Let's look at another example. Let's talk about digestion of food. Now the food that we eat, they are solid. Like a lot of food that we eat are solid. Let's say if we eat a burger, so the burger is solid. But what happens as the burger gets digested inside our body? So we chew the burger, break it down into smaller pieces, a lot of digestive enzymes act on the burger, and that's how the digestion process takes place. And as these reactions take place inside the body, the burger which was earlier solid in state also changes to other states. For example, it changes to liquid state, right? So digestion of food is one example where we see that there is a change in state as the chemical reaction takes place. Let's talk about burning of petrol or diesel in a vehicle. What happens? Now, as the fuel is burnt, we see that a lot of gases are emitted. In fact, you would have seen that as vehicles move from one place to another, that gases are emitted. So, evolution of gas is clearly seen. Besides that, we also notice a change in temperature. Now, as the vehicle operates, you will see that the engine and the parts of the vehicle become hot. Why? Due to an increase in temperature. So as chemical reactions take place, there is also a change in temperature. So these two phenomena are illustrated by this example of a vehicle. So burning of petrol or diesel in a vehicle shows that there is evolution of gas or change in temperature during a chemical reaction. Whenever a chemical change occurs, we say that a chemical reaction has taken place. Look at this example. Magnesium plus oxygen gives magnesium oxide. So what do we see here? Two different elements, magnesium and oxygen, they combine together to form a new thing which is magnesium oxide. So that's a chemical reaction. Now, all those substances that undergo the chemical change, they are called reactants. So in this case, magnesium and oxygen, they are undergoing the change, as in magnesium was earlier magnesium and now it became magnesium oxide, so it underwent a change. Similarly, oxygen was earlier oxygen and now it became magnesium oxide, so it underwent a change. So they are reactants, and the new product which is formed is called the product. So basically the new substance which is formed, or the output of this chemical reaction, is the product. Why do we even need a chemical equation? Shorter names, easier to write, and super easy to balance the equation. So this equation tells us why writing chemical equation is required or it is beneficial. So instead of writing magnesium plus oxygen gives magnesium oxide, we have simply used their symbols, and this made it like short, easy to write, and also balancing became easy. Now, why do we need to balance a chemical equation? That is something we'll discuss a little later. But for now, all you need to understand is why is chemical equation preferred, or why do we even talk about chemical equation? Now, this equation was anyways a short equation. Now, if we talk about slightly more complicated equations like this, where carbon monoxide combines with hydrogen to form CH3OH. So in this case, you see it is not just the symbols of the elements that is mentioned, the equation also talks about the state of each of the reactant and the product, and also under what circumstances this reaction is taking place. So we see that it's like a compact version which gives us all the necessary information, but in short. In fact, sometimes more complicated equations like this is a very popular equation of a process called photosynthesis, the process by which green plants prepare their own food in presence of sunlight using chlorophyll. So even in this case, we see that the reactants and the products are clearly mentioned, which states that carbon dioxide combines with water in presence of sunlight and chlorophyll to form C6H12O6, which is glucose, and oxygen is liberated during the process. And it also tells the states of each of these reactants and products. Right? So we see that looking at all of these examples of chemical equation, we really understand the need of chemical equation, even though we already had the concept of chemical reaction. So equations made it more convenient to write, easy to remember, and balancing was super easy. Now, as I was mentioning, states of chemicals. Now, that is very, very important. We must know what is the state of a particular reactant or a product. Now, even before we get into the different states and their abbreviations, let's understand why mentioning the state is important. Let's say we talk about, say, sugar. So let's say we talk about a reaction that takes place with sugar. I mean the sugar crystals. Let's say we talk about another reaction that takes place with sugar solution, as in sugar dissolved in water. Now, a sugar solution and the sugar crystals, are they exactly the same thing? Not really. I mean, the way they might react with other substances might not be the same. And that is why it is important to mention the state of a particular chemical. So whenever we are talking about an aqueous solution, as in a substance dissolved in water, the term aqua has been derived from water, and that's why it is called aqueous and is abbreviated as AQ. So whenever we're talking about any aqueous solution, we mention AQ. If we are talking about a liquid, we mention L. If we are talking about a solid, which is like insoluble, or a precipitate. So precipitate is the residue that is left behind. And if we are talking about a gas, it has to be G. So these are the abbreviations that we use to indicate whether a reactant or a product is solid, liquid, gas, or aqueous. So let us look at this equation and see if it is balanced or not. So what we understand so far is, for an equation to be balanced, the total number of atoms of each element must be same before and after the reaction. That means the total number of atoms for each element. So in this case, we have two elements, magnesium and oxygen. So the total number of atoms for each of these elements must be same on left hand side and right hand side, right? So let us suppose this is the reactant side, product side. So how many magnesium atoms do you have on the reactant side? 2. On the product side, 2. How many oxygen atoms do you have on the reactant side? 2. On the product side, 2. So that means both these elements are balanced and therefore the over equation is balanced. Let's take another example. Zinc plus H2SO4 gives ZnSO4 plus H2. So in this case, what are the elements which are involved? Zinc, hydrogen and sulfate. So zinc, if you talk about the reactant and product side, so we see that zinc is 1 on both sides, hydrogen is 2 on both sides and sulfate is 1 on both sides. So please note that oxygen is included as part of the sulfate group. So here also we see that all of these are balanced and therefore the overall equation is also balanced. So let's try a few more exercise. So here we have an equation Fe plus H2O gives Fe3O4 plus H2. So let's first identify the elements which are part of the equation, that is Fe, hydrogen and oxygen. So let's count the number of atoms for each of these on reactant and product side. So for iron on the reactant side we have 1, on the product side we have 3. Hydrogen on the reactant side we have 2, on the product side also 2. Oxygen on the reactant side 1 and on the product side we have 4. So obviously this equation is not balanced. Now what do we need to do if we want to balance this equation? Let's try. So in order to balance iron, we need to multiply by 3 on the reactant side so that both become equal. So that means we multiply by 3 on the reactant side. Okay, so now iron is balanced. Hydrogen is anyways balanced. What about oxygen? To balance it, we need to multiply by 4 on the reactant side. So here we multiply by 4. But the moment we multiply this by 4, we are also altering the number of atoms of hydrogen on the reactant side. So the number of atoms of hydrogen on the reactant side becomes 8. Right? So therefore, in order to balance hydrogen, we need to multiply by 4 on the product side. So here we need to multiply by 4. So now here you see, if you look at this particular equation, this is a balanced chemical equation. Let's look at the next example. So here we have carbon monoxide plus hydrogen gives CH3OH. So let's identify the elements which are involved there. One is carbon monoxide, hydrogen. Okay, so it's basically carbon, hydrogen and oxygen. So these are the 3 elements involved here. Right? Let's look at the count of the number of atoms on the reactant as well as product side. So carbon we have 1 on the reactant side, 1 on the product side. Hydrogen we have 2 on the reactant side, 4 on the product side. Oxygen we have 1 on the reactant side and 1 on the product side. So basically all that we see is we need to balance hydrogen in this case. So basically we need to multiply by 2 on the reactant side to balance hydrogen on both sides. So therefore we multiply this by 2 and now the equation that we get is a balanced chemical equation. Let's look at the third equation. CO2 plus 6H2O gives C6H12O6 plus 6O2. In this case again we have carbon, oxygen and hydrogen. Let's look at the count of the number of atoms on reactant and product side. So how many carbon do we have on the reactant side? 6. How many on the product side? 6. How many oxygen on the reactant side? 6 2s are 12 plus 6, that is 18. Product side 6 plus 12, that is 18. Hydrogen on the reactant side we have 12. On the product side again we have 12. So we see that this is already a balanced chemical equation. So we really do not need to do anything to balance it. So now that we tried balancing 3 chemical equations, let's look at the rules because these rules are important. Many a times you will notice that in an equation you try to balance hydrogen, meanwhile you end up spoiling the balance of carbon. When you try to balance carbon, you end up spoiling the balance of oxygen and so on. So it is important to understand the priority. So in any equation, balance the polyatomics first. Polyatomics, any such compound which is made up of more than one atom. For example, if you talk about sulfate, you talk about nitrates, right? So these are all, you talk about hydroxides, these are all examples of polyatomics because they are made up of more than one type of atoms. Now we consider something as polyatomic only if it is present on both the reactant and the product side. It shouldn't happen that it is only on the reactant side and not on the product side. Then the next priority is of metals. Then comes the non-metals, and in non-metals also hydrogen and oxygen should be at the last. So that's the priority list. Not only that, it is important to ensure that no fraction should exist in the final equation. For example, let's say that you get the equation in this format: 2 by 3x plus y is equal to z. So x, y, z are like just dummy numbers written here to represent the elements or the reactants and products. So in this case, how will you get rid of this fraction 2 by 3? So in such cases, you multiply the entire equation by the denominator. So what happens? You get 2x plus 3y is equal to 3z. And that's absolutely correct because now you have the same balanced equation without the fraction, right? So this is important. One very important thing is formula should not be changed. For example, let's say that you have an equation like this: hydrogen plus oxygen combined together to form H2O. Now, if you are asked to balance this equation, now you may think that okay, fine, then let me put a 2 here. So now it is balanced: H2, H2, O2, O2. But this cannot be done because H2O, because we have altered the formula altogether. So H2O is water. But the moment we make it H2O2, what is it? It is hydrogen peroxide. So they are two different things altogether and we just can't alter the formula therefore. So how do we balance it? So we multiply this by 2. So what happens? Oxygen gets balanced, and in order to balance hydrogen, we multiply this also by 2. So this is how we balance it, right? So that we do not alter the molecular formula. So let's try balancing a couple of chemical equations, and we start with the first one, which is a simple one. Nitrogen plus hydrogen gives ammonia. So in this case, we will quickly recap our priority rules. So the first priority goes to the polyatomics. So in this equation anyways, we do not have 1. The second priority goes to metals, and the third priority goes to non-metals. And in non-metals also hydrogen and oxygen at the end. Okay. So here what all do we have? We just have non-metals, that is nitrogen and hydrogen. So nitrogen will have more priority over hydrogen. So let's look at the count of atoms. So nitrogen 2 on the reactant side, 1 on the product side. Hydrogen 2 on the reactant side, 3 on the product side. So let's start balancing. So in order to balance this, we need to multiply by 2 on the product side. So here we multiply by 2. But the moment we do that, we are also altering the number of hydrogen atoms on the product side. So now the number of hydrogen atoms on the product side became 6. So now in order to balance hydrogen, we need to multiply by 3 on the reactant side. So here we multiply by 3, and this one is a balanced chemical equation. Let's try with the next one, which says CH4, that is methane, plus oxygen gives H2O plus CO2. So which are the elements involved in this case? Carbon, hydrogen and oxygen, right? So priority will be of carbon. All of these are non-metals, but we know that hydrogen and oxygen to be put at the end, right? So let's look at the count on reactant and product side. So carbon 1 on the reactant side, 1 on the product side. Hydrogen 4 on the reactant side and 2 on the product side. Oxygen 2 on the reactant side and 3 on the product side. 1 plus 2, 3. Right? So carbon is anyways balanced. Now, so the next comes hydrogen. So in order to balance that, we multiply by 2 on the product side. Right? So we multiply by 2 on the product side. So the moment we multiply by 2, we are also altering the number of oxygen on the product side. So that becomes 2 plus 2, that is 4. So this becomes 4. So now in order to balance oxygen, you need to multiply by 2 on the reactant side. So here we multiply by 2. So now this is a balanced chemical equation. Let's look at the next one. C4H10 plus O2 gives CO2 plus H2O. So in this case also the elements involved are carbon, hydrogen and oxygen. So let's look at the count of atoms. So carbon we have 4 on the reactant side and 1 on the product side. Hydrogen we have 10 on the reactant side and 2 on the product side. Oxygen we have 2 on the reactant side and 3 on the product side. So let's start with carbon. So in order to balance carbon, we need to multiply by 4 on the product side. So here it becomes 4. But the moment we do that, we are also altering the number of oxygen atoms on the product side. That becomes 8 plus 1, that is 9. So this becomes 9. Okay. So now let's try to balance hydrogen. So in order to balance hydrogen, we need to multiply by 5 on the product side. So that means we need to multiply by 5 here. So as a result, what happens again? The count of the oxygen atoms on the product side is altered. So now oxygen atom is 5 plus 8, that is 13. So this becomes 13. So now let's try to balance oxygen. So in order to balance oxygen, we need to multiply this by 13 by 2. So that 2 and 2 gets cancelled and this also becomes 13. Right, so here we multiply it by 13 by 2. Now, as such, the equation is balanced now. But the issue is that the final equation that we have arrived at has a fraction. And we do not want a fraction in a balanced chemical equation. Right? So how do we get rid of the fraction? By multiplying the entire equation by the denominator. So when we do that, we get 2C4H10 plus 13O2 gives 8CO2 plus 10H2O. So this one is a balanced chemical equation. Let's look at the next equation. AgNO3 plus MgCl2 gives AgCl plus MgNO3 whole 2. Now this is going to be a little interesting because we have a polyatomic here. So what is the polyatomic involved there? NO3. Besides that, we also have metals like Ag, which is silver, and magnesium, and we also have non-metals like chlorine. So topmost priority is polyatomics, then comes the metals, and then comes the non-metals. Right. So let's look at their count on reactant and product side. So NO3 is 1 on the reactant side, 2 on the product side. Ag is 1 on the reactant side, 1 on the product side. Mg is 1 on the reactant side, 1 on the product. Chlorine is 2 on the reactant side and 1 on the product side. So let's try to balance. So in order to balance the polyatomic, that is nitrate, we need to multiply by 2 on the reactant side. So this we multiply by 2. As we do that, the number of atoms of silver also changes on the reactant side. It becomes 2. Now let's try to balance Ag. So for that we need to multiply by 2 on the product side. So we multiply by 2 on the product side. So as we do that, we are also altering the number of chlorine atoms on the product side. So the number of chlorine atoms on the product side became 2 now. Right? So now we see that chlorine is balanced, magnesium was anyways balanced. So this is a balanced chemical equation. Look at the next one. H2SO4 plus KOH gives K2SO4 plus H2O. So in this case, what are the elements which are involved? So we have a polyatomic here, that is SO4 sulfate. Besides that, we have potassium, hydrogen, oxygen. So so we have written it already as per the priority list. So sulfate being polyatomic has the topmost priority, then potassium, then hydrogen and oxygen. So let's look at the count of the atoms. So sulfate is 1 on the reactant side and 1 on the product side. Potassium is 1 on the reactant side and 2 on the product side. Hydrogen is 2, not 2 but 3 on the reactant side and 2 on the product side, and oxygen is 1 on the reactant side and 1 on the product side. Now here you may ask a question that why is OH not considered as a polyatomic? That is because OH is present only on the reactant side and not on the product side. So only when a polyatomic is present both on the reactant and the product side, just like sulfate here, only then it is considered as a polyatomic. Otherwise, it is not counted as a polyatomic. Okay. So now let's start the balancing. So sulfate is already balanced. In order to balance potassium, we need to multiply by 2 on the reactant side. So that's what we did. Now as we did that, so the number of oxygen atoms and hydrogen atoms on the reactant side gets altered. So the hydrogen atom now becomes 2 plus 2, that is 4. So this becomes 4 and oxygen atom becomes 2. So now let's balance hydrogen. In order to balance hydrogen, we multiply by 2 on the product side. So this is where we multiply 2. As we do that, the number of oxygen atoms on the product gets altered and it becomes 2. So oxygen gets balanced. So therefore, this is a balanced chemical equation. Let's look at the next one. H3PO4 plus CaOH whole 2 gives HOH plus Ca3PO4 whole 2. So in this case, we have multiple polyatomics. So one is phosphate, the other one is hydroxide, that is OH. Besides that, we have metals like calcium and we also have non-metals like hydrogen. So let's look at the count of the atoms on reactant and product side. So for phosphate, we have 1 on the reactant side and 2 on the product. For hydroxide, we have 2 on the reactant side and 1 on the product side. Calcium, we have 1 on the reactant side and 3 on the product side. And hydrogen, we have 3 on the reactant side and 2 on the product side. Right? Let's start. So in order to balance phosphate, we multiply by 2 on the reactant side. So here we multiply by 2. The moment we do that, the number of hydrogen atom also gets altered. So the hydrogen atoms become 6 on the reactant side. Right? Now let's move on to hydroxide. So in order to balance this, we need to multiply by 2 on the product side. So here we multiply by 2. And the moment we do that, what happens? Hydrogen on the product side also gets altered. So it becomes 2. So there was a little error here. So earlier this was 1. So now it has changed to 2. Right? So in fact, when you do this yourself, you will be able to do it correctly. So earlier, so this was just by mistake, I wrote 2, but initially it was 1, but now it became 2. Okay. So now let's move on to calcium. So in order to balance calcium, we need to multiply on the reactant side by 3. So that means we multiply by 3 here. But an important catch here is that as we try to balance calcium, we destroy the balance of hydroxide. Because the moment we multiply by 3, the number of OH on the reactant side becomes 6. So that means this changes to 6. So if we really want to balance this, we further need to multiply the product by 3. That means here we further need to multiply it by 3. Now when we further multiply it by 3, what happens to the number of hydrogen atoms? That also gets multiplied by 3. So total number of hydrogen atoms on the product side becomes 6. Right? So as a result, the hydrogen atom gets balanced. So this is a balanced equation. So if you write the balanced equation, it will be somewhat like this. 2H3PO4 plus 3CaOH whole 2 gives 6HOH plus Ca3PO4 whole 2. So this one is a balanced chemical equation. Let's look at the next one. Now this is a different pattern altogether. So here instead of an equation, you will be given a reaction which is not written in the form of like the symbols. It's written in words like hydrogen plus chlorine forms hydrogen chloride. So we need to write a balanced equation for this. So hydrogen is H2, chlorine is Cl2, and this gives hydrogen chloride, that is HCl. So if we have to balance this, now will you be able to balance it? So I'm sure you'll be able to do it on your own, but still let's do it once. So chlorine will have more priority over hydrogen, and then the number of atoms of reactant side, product side, so number of chlorine atoms on the reactant side is 2, product is 1, hydrogen also 2, 1. So in order to balance this, we need to multiply 2 on the product side. So basically here if you multiply by 2, you get a balanced chemical equation. Let's try the next one. It says barium chloride plus aluminium sulfate gives barium sulfate plus aluminium chloride. So let's try to write it. Barium chloride is BaCl2 plus aluminium sulfate is Al2SO4 whole 3. This gives barium sulfate, which is BaSO4 plus aluminium chloride, which is AlCl3. Now, what are the elements or what are the species which are part of these equations? Now is what we are trying to do is balance. So one is sulfate, then we have metals like aluminium and barium, and then we have non-metals like chlorine. So let us look at the number of atoms of each of these elements on the reactant and product side. So we have 3 sulfate on the reactant side and 1 on the product side. We have 2 aluminium on the reactant side and 1 on the product side. We have 1 barium on the reactant side and 1 on the product side. We have 2 chlorine on the reactant side and 3 on the product side. So let's start balancing. So in order to balance sulfate, we need to multiply by 3 on the product side. So we multiply by 3 here. So as soon as we do that, what happens? The number of atoms of barium on the product side changes to 3. So this becomes 3. Okay, now let's move on to aluminium. So in order to balance aluminium, we need to multiply by 2 on the product side. So we multiply by 2 here. So as soon as we do that, we are again altering the number of chlorine atoms on the product side. So that becomes 6. So this becomes 6. Now let's try to balance barium. So in order to balance it, we need to multiply by 3 on the reactant side. So here we multiply by 3. Again, when we do that, the chlorine atom count also changes. So on the reactant side, the chlorine atoms become 6. So chlorine atom gets automatically balanced. So this is a balanced chemical equation. Let's move on to the next one. Calcium hydroxide plus carbon dioxide gives calcium carbonate plus water. So this can be written as calcium hydroxide, that is CaOH whole 2 plus carbon dioxide CO2 gives calcium carbonate, that is CaCO3 plus water, that is H2O. Right? So which are the elements which are part of it? One is calcium, the other one is carbon, hydrogen, oxygen. Why not hydroxide? Because it is not there on the product side. So now let's look at the count of atoms. So calcium, we have 1 on the reactant side, 1 on the product side. Carbon, 1 on the reactant side, 1 on the product side. Hydrogen, we have 2 on the reactant side and 2 on the product side. And oxygen, we have 4 on the reactant side and 4 on the product side. So 2 plus 2 and this side 3 plus 1. So you see it is already balanced. So therefore this equation doesn't need any further balancing because it is already a balanced equation. Let's move ahead with the next one. Write a balanced chemical equation with state symbols for the following reactions. So now we have one added work. So here not only we have to write a balanced chemical equation, we also need to mention the state symbols, like whether it is solid, liquid, gas or aqueous solution. Right. So let's look at this one. Sodium hydroxide solution. So sodium hydroxide solution in water, that means it is aqueous. Reacts with hydrochloric acid solution in water. So this is also aqueous. To produce sodium chloride solution, that is NaCl, again solution, so it is aqueous plus water. So water is obviously liquid. So we have mentioned the state symbols, and now all that we need to do is we need to balance it. So if you look at the balancing, sodium is already balanced. Oxygen is 1 on this side, is 1 on this side, so oxygen is also balanced. Hydrogen is 2 on this side and 2 on this side, so hydrogen is also balanced. Chlorine 1, 1, so chlorine is also balanced. So this one is a balanced chemical equation with state symbols. Let's look at the next one. It says solutions of barium chloride, that is BaCl2. It is a solution, so it will be aqueous. And sodium sulfate in water. So sodium sulfate is Na2SO4. Now this is also solution, right? So this is aqueous. Gives insoluble barium sulfate. Insoluble, that means it is not soluble. So it is not solution, so it is a solid. So this would be solid plus solution of sodium chloride, that is NaCl, aqueous. And now all that we need to do is balance this equation, and that I leave it to you as a task. So I'm pretty sure that you will be able to balance the equation. Now that you have learned all the tricks of balancing a chemical equation, here is a quick question for you. Try this out. KClO3 plus KCl gives KCl plus O2. Please try to balance this equation and put your answers in the comment section. Let's start with combination reaction. So what's a combination reaction? As the name suggests, combination, combine. When two chemical species combine to produce a single compound, that is called a combination reaction. This is also called as synthesis reaction because in this reaction, a new compound or a new product is synthesized or manufactured. Right? So the general format looks like this. A plus B forms AB. So a quick analogy to this could be, let us suppose this is Ronnie and this is John, and Ronnie and John, they share a lot of things in common, and that's how they group together and they are like best buddies. So they like group together to do their project work, they do group studies, so they play together. So it's like they combine together to form one single group. Right? So that's combination reaction. Now, some of the examples of combination reactions are quicklime plus water, or if you talk about hydrogen plus oxygen combining to form water, or sodium plus chlorine to form sodium chloride, or magnesium oxide formation, or carbon dioxide formation, or sulfur trioxide formation. So all these reactions that you see on the screen, they are all examples of synthesis reaction. Why? Because a new product is being formed. For example, water is formed, and it is formed from two things like hydrogen and oxygen. Similarly, magnesium oxide is formed from magnesium and oxygen. So these are all combination chemical reactions. Let us now move ahead with decomposition reaction. Decompose, what does it mean? Decompose means to break down or to split. So when a single compound decomposes to form two or more chemical species, that is known as a decomposition chemical reaction. So it is exactly the opposite of combination reaction. So here AB splits or decomposes to form A plus B. So let's say they are the best buddies. So when two best buddies, they say let's say they fight and then they separate out, they split. So that's decomposition chemical reaction. Some examples of decomposition chemical reactions are as follows. So as I said, they go exactly opposite of the combination reaction. So you can see that when water splits to form hydrogen and oxygen, that's a decomposition reaction. When hydrogen peroxide splits to form water and oxygen, that's a decomposition reaction. When ammonia splits to form nitrogen and hydrogen, that's decomposition reaction again. So all of these are examples of decomposition reaction. Now, you may ask a question that if we leave water in a glass, so will it decompose into hydrogen and oxygen? Of course not. So this decomposition would happen only under some specific circumstances. For example, water will decompose into hydrogen and oxygen only on electrolysis. Similarly, if you talk about copper carbonate, that is CuCO3, it breaks down to form copper oxide and carbon dioxide only on thermal decomposition. That means only when heat is given, only then copper carbonate would decompose into copper oxide and carbon dioxide. So these decomposition will take place only under some special circumstances. Let's move ahead and talk about displacement reaction. Displacement. So with the name, all that we could guess is, in this reaction, an element would displace another element from a compound. So displace, that means kicking someone out and taking its position. So that's basically what we mean by displacement in a chemical reaction. So this is how the general format would look like. AB plus C gives AC plus B. So if you see here, this element C kicks out B from its position and takes its position and forms a new compound AC, right? So you can take this example. Let us suppose these are dance partners. So they practice dance together and she is the instructor. So now the instructor wants to teach a particular step. So what she does, she takes the position of one of the dance partners. So you see the instructor who was here has kicked out this girl and took her position, right, to demonstrate a particular step or to teach a particular step. But this is what we mean by displacement. So when an element kicks out another element from a compound and takes its position. So some examples of displacement reactions are as follows. So if you look at all of these reactions on the screen, they are all displacement reactions. So here, let's randomly pick one of these and see if displacement takes place in them or not. Let's talk about sulfuric acid and iron. So you see H2SO4 plus iron gives ferrous sulfate, that is FeSO4 plus H2. So what's happening here? Iron is actually kicking out hydrogen from this compound and taking its position. So instead of hydrogen, you have iron now, and it forms iron sulfate. Right? Similarly, let's talk about this equation. Zinc plus HCl gives ZnCl2 plus H2. So here also we see that zinc is actually kicking out hydrogen from this compound and taking its position and forming ZnCl2. So we see displacement is taking place in each of these reactions, and that's why they are called displacement chemical reaction. Let's now talk about the fourth type of reaction, that is double displacement reaction. Now what happens in a double displacement? Now here it's like one element is kicking out another one from its position, and the other element is also kicking out the first one from its position. So in fact, two elements are exchanging their positions in their respective compounds. So that is called double displacement. So this is how the general format looks like. AB plus CD forms AD plus CB. So basically if you see, D is kicking out B from its position and taking its position and forming AD. Similarly, B is kicking out D from its position and taking its position to form CB. So in a way, we can say that B and D have exchanged their positions. So that's double displacement. So you can consider this analogy. Let's say these are the dancing partners, like two dance partners, two set of partners. Now what happens when they exchange their partners? It's like, you see, the females are still the same, but the guys, they have been changed. So they have interchanged their positions. So that's double displacement. So some examples, even before we talk about some examples of double displacement, there are some certain types of reactions which have different names, but they also fall under the category of double displacement. For example, precipitation reaction and acid-base reactions. So what happens in precipitation reaction? So in a precipitation reaction, two solutions are mixed together to produce an insoluble solid, which is called the precipitate. So as you see, solution A combines with solution B to form insoluble solid C, which is called precipitate, and a solution D. So that's precipitation reaction. Acid-base reaction is also known as neutralization reaction. And under this reaction, an acid combines with a base to form salt plus water. Now, why it is called neutralization? Because when an acid combines with a base, the acidic property is lost, the basic property of the base is lost, and both of them join together to form salt, which is neutral. And that is why it is called neutralization reaction. So, even before we talk more about what is precipitation and what is acid-base reaction, I think it will be a good idea to take examples of both of them. So here on the screen, we are seeing few equations, and they are all examples of double displacement. Let's look at the first one. HCl plus NaOH forms NaCl plus H2O. So in this case, what happens? In this case, we see that hydrogen chloride, which is an acid, combines with NaOH, which is a base, to form NaCl, which is salt, which is common salt, and water. So this is acid-base reaction. And here we see that double displacement takes place. How? Because this Na and this hydrogen, they exchange their position. So Na goes here to form NaCl and H comes here to form H2O. So they exchange their position. So that's double displacement. Similarly, let's look at the second example. AgNO3 plus KCl gives AgCl plus KNO3. So in this case also we see that, so these are both in the solution form. So two solutions combining together to form this insoluble solid, that is precipitate. This is white in color, so we get a white precipitate as a result of this reaction. But here also we see that the potassium and the silver, they exchange their position. Potassium comes here to form KNO3, silver goes here to form AgCl, right? So this is double displacement again. So what we understand is precipitation reaction and acid-base reactions, they are also double displacement reactions. Let's now move ahead with the last type of reaction, that is combustion reaction. Combustion means burning something. It could be a material like wood, it could be a fuel like petrol or diesel. So basically, when a combustible material, a material that catches fire and burns easily, when a combustible material reacts with an oxidizer to form a product, that is what we call as combustion. So examples of combustible materials are wood, diesel. These are all examples of combustible material. Now let us try to understand combustible chemical reactions with more examples. So let's say a combustible material is basically a hydrocarbon that consists of hydrogen and carbon. So when a hydrocarbon combines with oxygen, it forms carbon dioxide plus water. And as a result of this process, a lot of heat energy is also released. So these are combustion reactions. So let us look at some examples. Methane plus oxygen, or octane plus oxygen, or propane plus oxygen, ethanol plus oxygen, butane plus oxygen. So all of these, they are all hydrocarbons, and when they are oxidized, that is when they combine with oxygen, they produce carbon dioxide and water, and this is called combustion. So we have learned about the 5 different types of chemical reactions, and it's question time. So here is a quick question. Please attempt and post your answer in the comment section below. So you have to identify the type of this reaction. Na2SO4 aqueous solution plus BaCl2 aqueous solution gives BaSO4 precipitate, which is solid, plus NaCl aqueous solution. So please type your answer in the comment section of the video. I'm pretty sure that you would have identified the chemical reaction by now. So what are you waiting for? Type your answer in the comment section and do let us know. Not only the 5 types of reactions, there are many different types of chemical reactions that keep taking place in and around our life in so many ways. Some of the reactions like endothermic reaction, exothermic reaction, redox reactions, they play a very key role in our day-to-day life. And that is why we will dedicate this video to some of these very important types of reactions. Now, even before we talk about them, just understand the meaning of these words. Endo means inside. Exo means outside. Thermic, thermo means heat. Now, when heat is given out, that is exothermic reactions. When heat is taken in or heat energy is absorbed, that is endothermic reaction. Pretty simple. Endo is in, heat taken in, that is endothermic. Exo is out, heat given out, that is exothermic. So these are the 2 types of reactions. Now if we have to talk about examples, let us talk about say combustion reactions. So combustion reactions are all exothermic in nature. So they are all exothermic reaction because as a part of combustion reaction, a lot of heat energy is released. Heat is given out. So they are exothermic. Besides that, if you talk about this reaction where calcium oxide combines with carbon dioxide to form calcium carbonate plus heat energy. So that is again exothermic because heat is released as part of this reaction. Now what about endothermic reactions? Let's take this example. When magnesium combines with oxygen, it forms magnesium oxide. But for this reaction to take place, we need to provide heat. So if you remember, we actually heat the magnesium ribbon. So heat is an input in this case. So therefore, this is an example of endothermic reaction because we are giving heat as an input for this reaction to take place. So that's endothermic. Let's talk about the process of respiration. So respiration is an example of exothermic reaction. Can you say why? Now before that, what is respiration? Is respiration all about breathing? No, not really. So breathing is just external respiration. Breathing is only exchange of gases. But when we talk about respiration as a whole, it is external respiration, that is breathing, plus internal respiration. And what is internal respiration? Oxidation of food. So what happens is the food that we eat, that gives us energy. But how? By internal respiration. The food that we eat gets oxidized to release a lot of energy and also heat. And this is what happens as part of internal respiration. So that is why respiration is an exothermic reaction. And from where do we get this oxygen? It comes from breathing. So that's where we talk about external respiration. Right? So respiration as a whole is an exothermic reaction because energy is released as a part of this reaction. The next reaction that we want to discuss is redox reaction. Redox, reduction, oxidation. So what is reduction and what is oxidation? So oxidation, as the name suggests, oxidation, that means oxygen is getting added, that is gain of oxygen. Reduction, that means loss of oxygen. Very simple to remember. Oxidation is gain of oxygen, reduction is loss of oxygen. Now if you have to explain it in terms of hydrogen, so gain of oxygen actually means loss of hydrogen. So you can say oxidation is loss of hydrogen and reduction is gain of hydrogen. So just to keep it simple, just remember it in terms of oxygen. Oxidation, gaining oxygen, reduction, reducing or losing oxygen. Simple. Now let's take example. Let us suppose copper plus oxygen gives CuO, that is copper oxide. So what's happening here? Oxidation or reduction? So in this case, we see that copper is changing from copper to copper oxide. So copper is gaining oxygen. So we can say that copper is oxidized in this case. Let's take another example. Copper oxide plus hydrogen gives copper plus H2O. So what's happening here? Copper oxide is changing to copper. That means copper is losing oxygen. So we can say that copper in this case is reduced. However, in this case, we see that hydrogen is changing from hydrogen to water. So hydrogen is actually gaining oxygen. So we can say that hydrogen in this case is oxidized. So if you actually look at this reaction, we see that one element is getting reduced, the other element is getting oxidized. So that means oxidation and reduction are taking place simultaneously. This type of reactions are called redox reaction. That is why they are called redox. That is reduction, oxidation taking place side by side. So that's redox reaction. Now let us look at some examples of redox reaction from day-to-day life. One such example is corrosion. The best thing that you can think of is rusting of iron. So what happens in rusting? A reddish brown layer appears on the surface of iron articles, right? And from where do you get that layer? So that layer is nothing but oxide of iron. Now when these iron articles are exposed to air or moisture, they get oxidized just in this way. So iron combines with oxygen to form iron oxide, and this Fe2O3 is nothing but rust. So this oxide of iron is reddish brown in color, and this is what we see as rust over iron articles. So rusting is a result of redox reaction taking place. Now, can you answer this? Why do we apply paint on iron articles? To prevent rusting, because the moment we apply paint on iron articles, we are in a way trying to break the contact of iron with the oxygen in the surroundings, and that's how we are trying to prevent rusting. So that's the reason we generally paint iron articles. Another interesting example of redox reaction in our day-to-day life is rancidification. Difficult name? I'll make it easy for you. The word rancid means something with unpleasant smell or unpleasant taste. Let's talk about something which we use in our day-to-day life. I'm pretty sure that you often go to shop to buy a packet of chips or any kind of snack item, and your parents always advise you to buy the airtight packet, somewhat like this, inflated like a balloon, right? Why? That's because when the packet is airtight, the material inside it is prevented from oxidation. So it doesn't react with oxygen and doesn't get rancidified, and it stays fresh. In a similar way, you would have seen that when your mom or your grandmom prepares pickles, they put a lot of oil inside it. Why? So that the pickle don't spoil and can be preserved for a longer period of time. How? Because putting so much of oil, again, prevents the contact of air with the items present inside, and hence prevent oxidation, and hence prevents rancidification. So in this way, we see that in a lot of things around us, like in most of the materials that we store in our kitchen, we prefer to use airtight containers just to prevent rancidification. Give it a quick thought. Sometimes when you end up buying a packet of chips which is not airtight, as in it is not at all fluffy, what happens? When you open that packet, you see that you get a bad smell of oil in the chips, right? Why is that? That's because of rancidification. So this was one excellent example of redox reaction in our day-to-day life, and I'm sure that you would have noticed, and if you haven't, try to notice it from next time, that most of the food materials that we want to preserve for a longer period of time, especially in our kitchen, we store them in airtight containers. With this, we reach towards the end of this lesson on chemical reactions and equation, and I hope that you liked this. Do share your feedback in the comment section. We will be eagerly waiting for your feedback. See you all very soon with a new topic, with a new video. Till then, bye-bye.